Now moving towards another concept, and that is quality. Quality is defined as the mass of the vapor divided by the total mass. So it is the ratio of the mass of the mixture which is in vapor to the total mass. So that means, like, if I'm saying like the what is actually quality, so quality X is defined as the total mass of the vapor present with the total of the liquid and the vapor, total mass of the liquid and the vapor. Uh, it is the amount of how much the vapor has been. So the total vapor, which is actually, if I'm saying like, if I'm talking about the, and that's, we define it inside the vapor dome. So that means like, if at this point, let's say point A somewhere, uh, the amount of vapor over here is totally zero, and over here the amount of vapor is 100%. So that means like the quality, if would be X would be actually zero if we have got the mass of the vapor as zero. The quality would be 100% if the mass of the vapor is equal to the mass of the vapor is 100%. So that if you put in this equation, so that's quite clear. Like, if I've got the mass of the vapor as zero, so that means like the quality would be zero. If I've got the mass of the vapor one and there is no liquid in it, obviously, so the total mass would be, the total quality would be 100%. So the quality moved from 0% towards the 100%, or if in other words, the quality moved from 1 to, sorry, 0 to 1. So 0 is defined when we are having no vapor in it, and 1 is defined when we have got a total vapor, or it is the saturated vapor. uh, and obviously we have got from is moving, the quality move from 0 to 0 to 1. uh, Quality also is in some of the book is also referred as the dryness factor. 1 minus 1 is actually called as the moisture, and obviously it become like this. Let's say if sorry, we need to define one more thing. Like, now the volume at saturated liquid volume, sorry, we call it as Vf, and saturated vapor we call it as Vg. So the saturated liquid volume is called as Vf, or saturated liquid, saturated vapor is called as the Vg. And the obviously the quality move from Vf towards the Vg. If Vg is totally, if we have got total Vg, we have got the 100% quality, and if we have got total Vf in that mixture, we would be having a quality which would be 0%. Let's say if I'm interested in finding a volume somewhere over here, be over here. So obviously, the by graphical, if I would say like, so that mean like I would be defining quality X somewhere. So let me draw it like this. So if I'm interested in finding the volume over here, V, so it is the volume, this volume, which is some percentage of this one. So that means like percentage of Vg minus Vf something, multiply by that percentage X. So that X is what we call it as a quality now, plus this volume, which is over here, which is Vf somewhere from 0 to Vf. So that means like Vf is there. So if I'm writing it down, so that means like the equation would be Vf plus X Vg minus Vf. Vg minus Vf is mostly referred as Vg, Vfg, sorry, and this is actually quality of the, sorry, the volume of the mixture, or the evaporation volume. Now moving forward to another concept, and if I'm sorry, yeah, sorry, writing the whole, sketching the whole thing on a TV diagram, you can imagine like we have got the saturated liquid line now over here, we have got the saturated vapor line over here, we have got the two phases mixture, we have got the critical point, we have got the superheated region, we have got the compressed region, and obviously inside the vapor dome we have got the temperature and pressure which are constant, and we have got the temperature moving from low to high over here. We get saturated over here, and then obviously again from low to high over here. This is what we call it as a TV diagram. Now if you draw the same thing on a PV diagram, which mean like keeping the temperature constant and changing the pressure, so the graph would be something like this. Let me elaborate it a little bit in different way. For example, if you have got a gas somewhere, liquid, I'm saying like the steam somewhere, and that is definitely in a gaseous state. So if you put a pressure on that one, if you increase a pressure on it by keeping the temperature constant, so if you increase the pressure on it, so that liquid, that gas will try to condense actually. So it will actually, the gas will try to decrease its volume until when the volume would be decreasing, when it actually reach the saturation point. And once it reaches the saturation point, the condensation would start. Once the condensation is starting, the temperature would remain constant, and also the pressure is remain constant. As I said, like it is at the constant um, temperature line. So the temperature will be constant and the pressure will be constant. So we are going from the gaseous towards the liquid region. So now if you once all of the gas is converted to liquid, now if you further increase the pressure, it will be increasing pressure on the liquid obviously, and the pressure would be increasing. But if you can imagine, the volume of a liquid by increasing the pressure is changing, but not so much. So that will be the graph would be something like this. So this is a little bit, I've explained it a little bit differently, but if you can imagine, like if I've got a liquid and you are decreasing pressure on the liquid, so it will be actually expanded towards the saturated liquid, then towards the saturated vapor, and obviously to a superheated condition. So this is what we call it as a pressure and volume diagram. Now if this experiment is performed like a pressure less than 0.6113 kilopascal, the ice in fact directly goes into vapor, and that process is called as sublimation. um, Let me draw all these lines on a single phase diagram or a single plane, PT plane. Now remember, like we did actually sketch a PT diagram somewhere here, and that PT diagram was between liquid and gas. Now we can also draw a PT diagram between solid and liquid. So it will be something like this. And also we can draw a PT diagram between solid and gas. That is what we call it as a sublimation, if I did said. So now if I'm looking at this one now, so that will be liquid region. That would be the gas region, as I said earlier now. So now if I'm drawing a liquid and sorry, if I'm drawing another line, and that is line between the liquid, between the solid and liquid. Now this line can be called as the melting line. If I'm going from the liquid to solid, this kind line can be called as a freezing line. This line can be also called as a solid and liquid equilibrium line. So this is the phase diagram between the phase line between the solid and liquid, and this is actually the fusion line. Call it as a fusion as well. uh, it can also be, we can also draw a line, another line, and that will be if I'm saying like if I've got a pressure which is less than 0.613 kilopascal. Now the solid will be directly converted to gas. This process is called as the sublimation, or the gas will be directly converted to liquid. This process is called as deposition. So that line is called as the sublimation line, um, and solid gas line or deposition line. You can call it differently, but definitely that's the phase boundary between the solid and vapor. I did draw this thing like this line, solid and liquid line, differently than this line. This is actually sketch of water. Water has a property that when it actually freezes, the volume is expanded. So there are many material, when it freezes the volume is decreasing. So when the volume is increasing, actually when it be from liquid to solid, the line would be a little bit tilted backward. And if it is actually decreasing, the volume is decreasing, the line will be tilted forward. So make sure like there is a little bit difference. We can actually relate them in a literature principle, but that is actually some advanced topic that would be you will be doing in a thermo too if you people are interested in that one. So this is what we call it as a uh, phase diagram, and that is phase diagram of a water. One point which actually we did miss, like this point, which actually all the three equilibrium line coexisting, or the equilibrium coexisting, it is called as the triple point. For water, it is the triple point is 0.613 kilopascal and a temperature of the 0.01 degree centigrade. At this point, later on, we will understand that at this point, the energy, the internal energy of our water is taken as zero, and we call it as a starting point of our energy from this one. I hope you understand this lecture. If you have got any question in it, you can post it on a class Google Classroom, and I would be able to answer that one. Thank you very much. Have a nice time.